Good morning, students. Today we are going to discuss about coordination complexes. So before going into this topic, first we need to understand the history behind how these coordination complexes were discovered. So Werner is the father of coordination compounds. So we just will have a brief history about how he discovered these coordination complexes. So generally, when you add two different salts together, in a stoichiometric or superstoichiometric amount, they will just come together and become more stable. Okay, for example, you take potassium chloride, magnesium chloride, okay, and it just forms a double salt. So you have two salts you are adding up and it is called as double salt, carnallite. But when you add copper sulfate with ammonia in the presence of moisture or water as a ligand, you form a tetraamine copper 2 sulfate monohydrate. So the key difference between these two, for example, are the addition compounds. In this case, we call this as an addition compounds. In this case, we call it as a coordination complex. So what is the key difference between these two? For example, those double salts are those which will lose their identity. After it forms that carnallite, the salt, if you put it back into the solution, it will just dissociate and it will lose their identity. Okay, meaning that it will come back as a potassium chloride and magnesium chloride in principle. Whereas the metal complexes, once it is formed, this will retain this complex formation and that will retain its identity in the solution. So this is complexes. So when Werner were discovering this one, so he wanted to explain why these complexes or so-called double salts retain their identity in the solution, because that is the discovery phase, right? So if you take this particular, copper, so this is how the complex formation was, in equilibrium. So this will come to the point later. So Werner, he was able to explain this behavior using two, bonding, nature of bondings, and he concluded that in complexes the metal shows two different types of valency. Primary valency is something which are non-directional. Okay, so you will understand more when we are talking about the geometry of metal complexes. So the complex commonly exists as a positive ion. Okay, so the primary valency is nothing but the number of charges on the complex ion. This is what he termed as a primary valency, and the secondary valency, they are directional, and the number of secondary valencies equals the number of ligand that is coordinated directly to the metal. Let's say you learned about tetrahedral complexes, square planar, octahedral. There are a number of coordinations. Okay, that is called as a secondary valence. So these are the basic things which you might have studied during your +2 class. So how Werner proved that this is indeed a metal complexes. So what he did is he treated cold solution of coordination complexes with silver nitrate. So what is the need of silver nitrate? When the chlorine is present, this chloride will be precipitated as a silver chloride. So the stoichiometric of this particular silver chloride, which is precipitating, can be quantified. It was done in the early days. So this is how we have quantified. For example, he has taken the salt, and when you treat the silver nitrate, they obtained 3 equivalents of silver chloride. Whereas this particular compound, when treated, he got 2 equivalents of sodium chloride, and so was the case. So when the 3 chlorines are ionic, okay, and hence they are precipitated by the silver chloride by silver nitrate. So what does this mean? So when you have this, coordination sphere, the square bracket, outside you have chloride, only one chloride is present. Okay, so that is the meaning of this one. So that is how we have quantified it. For example, in this example A, how many equivalents of silver chloride you expect? 3, because 3 equal chloride ions are present outside the coordination sphere, whereas in the case of B, you are expected 2 equivalents of silver chloride to be precipitated. So this is how Werner quantified how many chlorides are present outside the square bracket. Also he did some of the electrical conductivity, because the ionic conductivity, okay, in a solution depends on the concentration of the solute which you are going to use, and also the number of charges on the species. So these are the two parameters which affects the electrical conductivity. So when you take lithium chloride, for example, you have one lithium ion La plus and one chloride ion. So you have two charges. So you will get a electrical conductivity for that particular two charges. Whereas in the case of calcium chloride, you have calcium 2 plus 2 chlorine ions. So totally you have 4 charges, but you get the conductivity for this species, so on and so forth. Okay. So based on this electrical mobility or the conductivity, he was able to assign the primary valency and the secondary valency for the complexes. So this is how this coordination, complexes formation was discovered. But people were trying to understand the behavior of these complexes or its physical property, chemical property, etc. So why we have to worry about these properties? For example, when you have a metal complexes, if you want some specific property, let's say it should be magnetically active, okay, you want to tune the magnetic property, you want to change the color for various applications, let's say OLEDs kind of applications. So we need to understand the underlying principle of why such complexes are colored or magnetic and so on. So the property, if you don't understand, we will not be able to fine tune those properties. So the key thing is we need to understand the complexes. Towards that, there are several theories were proposed to understand these metal complexes, or coordination complexes to be precise. So one is the valence bond theory. Okay. So in the limitations in the valence bond, okay, so usually a theory is proposed to understand what is already existing. Okay. So if you are not able to completely describe what is observed, so that particular theory fails. For example, valence bond theory, there are a couple of limitations. So most transitional metal complexes, okay, formed are colored, but this particular BBT theory was not able to explain any particular explanation for why these metal complexes are colored. And second, in particular, they have a magnetic properties which can be modulated when you change the temperature. So these are the two important major limitations that is present in the valence bond theory. Other than that, it was able to tell most of the properties related to the metal complexes or coordination complexes. So these limitations enabled or pushed the scientists to have other theories, that is what crystal field theory. So after this crystal field theory was established, there is no other theory evolved after this one. Why? Because the crystal field theory was able to explain all the properties or all the questions which is required to understand the properties of the coordination complexes. So what are the salient features of this crystal field theory, for example? So the attraction between metal and the ligand, they are considered as a purely electrostatic in nature. Okay, so for example, it is only about charges, so plus minus kind of a purely electrostatic. So bonding between these two can be an ion-ion attraction or ion dipole interaction. So these are the salient features or assumptions that was put forth while proposing the crystal field theory. So ligands, they are treated as a point charges. So the d orbitals on the metal all should have the same energy level in the free atom. Okay, before the ligand approaches that particular metal also, the d orbitals on the metal should have the same energy level. Okay, so coming before even going into the concept of d orbital splitting in the coordinate CFT theory, first we need to just recap what is orbital. Orbital is nothing but the probability of finding an electron in the three-dimensional space, right? So where the electron is resided, that is what we call it as orbitals. So we have four different orbitals, okay, S, P, D and F. So S electrons, S orbital, you have only one S orbital which can hold 2 electrons. P orbitals, we have 3 different P orbitals, Px, Py, Pz, so that can hold 6 electrons. Like that, D orbitals, we have 5 different D orbitals, dxy, dyz, dzx, dx square minus y square, dz square. So these 5 orbitals can hold 10 electrons. So if you take any d system, you may have the variation of having d0 to d10. So this is the broad spectrum with which we are going to understand these particular coordination complexes. We are specifically interested more on the 3D orbitals, which is like a classic or the most studied, coordination complexes. So as I said, d orbitals, the orbitals meaning the probability of finding the electron in the space. Okay. So as I also mentioned, we have 5 different d orbitals: dxy, dyz, dzx, dx square minus y square, and dz square. Okay. So now we will come to the concept of d orbital splitting. So even in the salient features, what we have mentioned is the d orbital should be in the degenerate energy. It means they have identical energy, the d orbital. So that is what, when you plot against the y-axis, these are the 5 different d orbitals. They are exactly identical in terms of its energy level. Okay. So this is a metal space. For example, now you assume that you have a octahedral complex. Okay. So octahedral means you know that we have 6 ligands which is approaching the metal in the 3-dimensional space in the octahedral space, right? So when we have these 6 dots, that is 6 ligands coming in the 3-dimensional space, the metal also have electrons, the ligand also have electrons, right? So there is a electron repulsion happens between the electron which is present in the d orbital versus the electron present in the ligands. But remember, these d orbitals, for example, dxy, yz, zx, the approach with which it is going to approach the metal is different from the way this dx square minus y square and dz square. Why? Because if you look at this particular figure very carefully, the dxy, the orbitals are present in between the axis, in between x and y, right? So you see the y-axis, x-axis and y-axis here, the orbitals are present in between the axis. So in between x and y, in between z and x, in between y and z. So these orbitals are in between the axis, whereas in the case of dx square minus y square, you can see this is the axis, so the orbital is along the axis. So x square minus y square, you have orbitals wherein it is present along the axis. So this z square, it is difficult to visualize, but at least you can see in the z square how it is looks like, right? So it is the along the axis. So whenever you have a metal and you have electrons which present in the ligand is approaching the electrons present in the metal. So this approach is can be categorized into 2 different. So the orbitals with in between the axis, along the axis. Okay. So when you have the interaction between electron of metal in between the axis of this particular ligand in the octahedral geometry. So this is more important. So the geometry is more important where you have very less interaction or repulsion between electron, whereas we have more repulsion in the dx square minus y square and dz square. Always remember the energy of any state is conserved. So as soon as the ligand is approaching the metal, because of this electron repulsion, in between the axis, now it is going to increase the energy of this particular orbital. Since the energy is conserved, 3 orbitals dx square minus dx square xy yz zx, this approach will stabilize the interaction, whereas the x square minus y square and z square is going to destabilize this interaction. So that is what is pictorially represented in this particular diagram. It looks very simple and classic, but understanding this is really important. So I have taken a d orbital, a metal which has a d orbital, and the energy is degenerate, and this degeneracy is only got disturbed, okay, or got splitted only because there is a ligand approaching in the octahedral geometry. Okay. So in this case, dx xy yz zx, where the electrons are present in the orbitals are along the axis. Okay, along the axis you have a stabilization effect. Because this is in between the axis, you have a destabilization effect. Okay. So the degeneracy of d electron energy state is no more degenerate. It got split. So this is what we call d orbital splitting in coordination complexes. So specifically in the octahedron geometry with this particular example. So this is just to recap. This y-axis is the energy. You have a degenerate energy. After the ligand started approaching the metal, the degeneracy of the d electrons got split. So this is what we also represented in a different way with more details. As I said, you have the energy plotted, degenerate d orbitals. Now it got splitted. As I mentioned, the energy is conserved. So how much ever you stabilize through these orbitals, that much it got stabilized. It should be destabilized on the other hand. Then only you will have the conservation of energy, right? So this 0.4 and 0.6, these are not arbitrary numbers. So this is the barycenter with which the d orbital initial energy level was. So as we know, in every single orbital you can have 2 electrons, right? So theoretically you can accommodate 6 electrons in dxy, yz and zx. So 6 electrons can be accommodated, and this 6 electron can have a stabilization effect. So whatever the stabilization happens with 6 electrons should be destabilized by only 4 electrons, because you have 2 orbitals. Each orbital can have only 2 orbitals. So the quantum with which it can stabilize, for example, 6 electrons of stabilization of 0.4, 6 fours are 24, 2.4 stabilization is happening with dxy, yz and zx. The same quantum of destabilization also happen, because here theoretically you can have 4 electrons. So 4 electrons into destabilization of 0.6, that is also 2.4. So generally a negative charge is given for stabilization effect and a positive charge is given for the destabilization effect. So that's a classic terminology which is utilized in the coordination complexes. So in this particular splitting, so you have an octahedral d orbital, ligands is approaching, you have a degeneracy splitted, d orbital got splitted, and now you have two set of orbitals, T2G and EG. That is what is mentioned. T stands for triply and E stands for doubly. Okay, so G in this case, what we call is a red, which is a symmetry element. So this G is only used in octahedral complexes, not in the tetrahedral complexes. Okay, so we need to understand why this is this particular G terminology is given for the octahedral complexes. So this can be best better understood. This can be very easily understood using the geometry. When you look at the geometry, you will have a better understanding on it. So that particular gerate, which is a symmetry element, so I will discuss in the next coming slide. So this is simplest summary. I have a degenerate d orbitals. As when the ligand approaches the metal, the degeneracy is lifted, d orbital got splitted, and this leads to two different subset of orbitals, xy, yz, zx, where the electrons are approaching in between the axis, that is giving the stabilization effect, whereas you have a dx square minus y square and this where the orbitals are in between the axis and you have seeing the destabilization effect. Okay, so this particular splitting, so right, so now this particular d orbital got splitted. So this particular splitting of d orbital depends on various factors. Okay, the very first factor that affects the d orbital splitting is the oxidation state on the metal atom. So when you are talking about copper 2 plus versus copper 3 plus, for example, okay, within the given same set of ligands. So when the oxidation state is more, okay, higher the oxidation state, that would lead to larger splitting of d orbital. So this particular gap between the T2G and EG will be smaller in terms in the copper 2 plus, and then it will be more with respect to the copper 3 plus. So higher the oxidation stage, higher is gonna be the splitting of d orbitals. Okay. So this is the first factor which is going to affect your d orbital splitting. Second is the size of the d orbitals. For example, when you move from top to bottom in the periodic table from 3D series, 4D series and 5D series. So this particular size of the d orbital, when you come from 3D to 4D to 5D, as the size of the d orbital increases, your d orbital splitting also increases. Okay. And then we also have the geometry. If it is a tetrahedral complex or a square planar complex or an octahedral complex, so the geometry also dictates the d orbital. So these are the three important factors that affects the splitting of d orbitals.